Welcome to the Walton Pi. What you are about to see is a test review held for calculus students that covered arc length, surface area, centroids, sequences, and series. So let's get started with some series stuff, because those are always fun. So let's find let's zoom in a bit. Let's find the radius of convergence. For the series going from n equals 0 to infinity of n x to the 2n minus 1 all over 4 to the n. So if we were to try and figure out the radius of convergence, so we are looking for r. This is going to be, if we look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, this is going to be equal to 1 over r times the absolute value of x. So if we go through and figure this out, we look at the limit as n goes to infinity, we get the absolute value of n plus 1 x to the 2n plus 1 all over 4 to the n plus 1 times 4 to the n over n x to the 2n minus 1. Well, this is equal to the limit as n goes to infinity of, let's see, we are left with a 4 on the bottom. For n, we have an n plus 1 on the top, and we have x squared. So that is what we are left with. So this is equal to the limit as n goes to infinity of the absolute value of n plus 1 over 4n times absolute value of x squared. And so we end up getting, this is going to be equal to a 1/4 absolute value of x squared. So that tells us that our radius of convergence is going to be 4. So r equals 4. Alright, let's do another one. Let's figure out about some conditionally convergent stuff. So we want to know which is conditionally convergent. So we have the sum, sum from n equals 2 to infinity of -1 to the 2n divided by n plus 1. We have the sum from n equals 3 to infinity we have the sum from n equals 1 to infinity of the natural log of 1 over n. We have the sum from n equals 1 to infinity of sine of n over 3 to the n, and then we have the sum from n equals 1 to infinity of n times -1 to the n all over n squared plus 5n plus 1. So we're trying to figure out which of these is going to be conditionally convergent. So conditionally convergent, that is when we are looking at a limit so conditionally convergent is if the series converges where we are looking at this series directly, but the series of absolute values of a sub n's, this diverges. So we're looking for which of these is going to have the series when we take the absolute values, when that's going to diverge. Because it turns out all of these are going to diverge or converge as they are written. So we are looking to see which one is conditionally convergent. So we are looking to see which of these diverges when we take the absolute values. Well, first off, if we look at this first one, this one is actually going to diverge if we take the absolute values, because the sum of 1 over n plus 1, that diverges. But notice that it already diverged, because negative 1 to the 2n, that's always going to be 1. So this first one always diverges. So this one is actually divergent as written. It's not conditionally convergent. The second one is going to converge either direction, because if we look at the sum of 1 over n squared minus n, this is going to be less than the sum of just 1 over n squared, and this is convergent. So that tells us that this series is also going to converge. So this one is just plain old convergent. If we look at the next one, the natural log of 1 over n's, and just adding up all of those, we are just adding up more and more infinite negative values, because natural log of 1 is 0, natural log of a half is negative, natural log of a third is even more negative. This one is also one that's actually divergent. If we look at the sine of n over 3 to the n, if we take the absolute values of those, this one is going to be, so the sum of the absolute value of sine of n over 3 to the n, that's less than or equal to the sum of 1 over 3 to the n, which converges. So this series converges either way. And this last one, by process of elimination, should be conditionally convergent. But if we go and look to see why that one is conditionally convergent, let's go into that one a little bit more. So this series is equal to the sum from n equals 1 to infinity of negative 1 to the n over n plus 5 plus 1 over n. So multiplying the top and bottom by 1 over n, that's going to give us this. And now what we can do is we can say, well, we can increase the denominator. And so if we decrease the denominator, that increases the fraction. So if we want to find something that's bigger, we want to decrease the denominator. So if we decrease the denominator, we can say, well, this is smaller than negative 1 to the n over n plus 5, which is smaller than negative 1 to the n over n. Whoops, forgot the sums in front. So those sums in front give us this, and this is going to be conditionally convergent. And in fact, it would work the same way if we were to just go straight from this one to the sum of n over n squared plus 5n plus 1. This is less than the sum of n over n squared, which is equal to the sum of 1 over n. This diverges, but this converges, which tells us that this is conditionally convergent. So that's how we can get that one. Let's see if we can do another one. Let's look at, let's use the alternating series estimation theorem. So alternating series estimation. So if we are wanting to estimate a series, so let's say that we are trying to estimate, we have negative 1 to the n minus 1 all over 2n factorial. The alternating series estimation, that says that the remainder of the nth sum, so this is n equals 1 to infinity. Yeah, n equals 1 to infinity. So the nth estimation is equal to the absolute value of s minus s sub n. So the actual value of the sum minus our nth approximation. That is going to be less than or equal to the absolute value of the inside term, so like b sub n, if we are looking at the sum of a negative 1 to the n minus 1 b sub n. So this tells us that our b sub n is just the 1 over 2n factorial. So if we want the so we want to estimate, I don't know, within 0.001, so that's 1 in 1,000. That tells us that we want our remainder to be less than or equal to 1 in 1,000. So we are just going to force b sub n to be in between. So we get 1 over 2n factorial is less than or equal to 1 over 1,000, which means that we need 2n factorial to be greater than or equal to 1,000. So let's just figure out what 2n factorial is. So we got n, 2n factorial. So when n is 1, that's 2 factorial equals 2. When n is 2, that's 4 factorial equals 1 times 2 times 3 times 4, that's 24. 3, that's going to give us 6 factorial. So that's 24 times 5 times 6 equals 24 times 30 equals 720. So that tells us that 4 at 8 factorial is going to be much bigger, and whatever that is, this is something that is bigger than 1,000. So that tells us that we can estimate it pretty accurately, let n equal 4. Let's try and do one where we are looking at a power series. So let's say that we have the series n equals 1 to infinity, and no, it should be n equals 0. We are looking at the series n equals 0 to infinity of some constants times x minus 3 to the n, and we know this converges when x equals 6, and we know it diverges when x equals negative 2. We want to know where does this series converge for sure. So we need to know where can we guarantee it'll converge. Now, because this is a power series, this is of the form the sum of some constants times x minus x naught to the n. So this tells us that x naught equals 3, which means that this is where it's centered. So we know it is centered at x equals 3. So if we were to look at a number line, we know that right here at 3 is the center. We also know that if we go out 3 more, right here to 6, we know it converges. So that tells us that the radius of convergence has to be at least 3. So that means going backwards 3, it should at least go that far. So we know that everything up to 0, we don't know if it includes 0, but everything from 0 all the way to 6, so all of this space in between here, it is guaranteed to converge. The other thing we know is that back here at negative 2, it does not converge. So that just tells us that it does not converge past 5. So if we go 5 past 3, so this would be at 8, everything past 8 is guaranteed not to work. Now, this does leave us a couple areas where we're just not sure what happens. So we don't know if between -2 and 0, or even at 0, as well as anything past 6 up until we reach 8, we just don't know what happens there. So right here we don't know what happens, right here we don't know what happens. But we are guaranteed that on the interval 0 to 6, it converges. That is a guarantee. Anything outside of that, we're not really sure. We know that past 2 and past 8, it definitely does not converge. But between -2 and 0 and between 6 and 8, we just don't know. We would need to be able to know a little bit more to know if it would converge there or not. Let's go through and talking about power series, let's try and find the power series of something. So let's say we have f of x equals the natural log of 1 minus 3x. We want to find a power series form. So, and let's centered at x equals 0. So we can always write f of x as the sum from n equals 0 to infinity of our nth derivative of f evaluated at x naught divided by n factorial times x minus x naught to the n. That is always going to be true. So the pieces that we know x naught, so x naught is going to be 0, so we know those two pieces. N is just going to be our index, so that's something that is fine. What we have to do though is we have to calculate what are our derivatives at x naught. So we can go through and figure out these different pieces. So we need to know what is f of x. Well, that's the natural log of 1 minus 3x. So that tells us that f at x naught equals 0. That's going to just be the natural log of 1, which is 0. If we look at f prime of x, well, that is going to be the derivative of the natural log of 1 minus x. So 1 over 1 minus 3x times the derivative of 1 minus 3x, so a minus 3. So f prime of 0, that is going to be negative 3 over 1. That's just equal to negative 3. F double prime of x is going to just be the derivative of negative 3 over 1 minus 3x. Notice this is 1 minus 3x to the 1. So this is going to give us a negative 1 times negative 3 all over 1 minus 3x. This is now raised to the 2 times the derivative of 1 minus 3x is another negative 3. So f double prime at 0 is going to be a negative 3 squared times negative 1. If we go through and figure out f triple prime of x, that's going to give us, we have a 1 minus 3x cubed on the bottom. We now have a negative 1 times negative 2 times negative 3 cubed. So f triple prime of 0 is going to be negative 3 cubed times negative 1 times negative 2. And now we're going to try and see if we can predict a nice pattern. So one nice thing that we have is we have negative 3 squared, negative 3 cubed. So we are probably going to say that f to our nth derivative at 0 is probably going to have a negative 3 to the n. Because when n is 3, we got negative 3 cubed. When n was 2, we got negative 3 squared. N was 1, we got negative 3, and so on. The next thing we have to do is we have to figure out what are we doing with the rest of these, because we have this negative 1, then we have a negative 1 times negative 2, then the next one we're probably going to have a negative 1 times negative 2 times negative 3. So this tells us that we are probably going to be having these negatives are just canceling out. So let's see what our overall negative is. So we have this one is negative, this one is negative squared times a negative, so that's negative. Negative cubed times two negatives, that's always negative. So let's rewrite this as negative 1 times 3 to the n. So then we are left with just we have 1, 2, the next one we're going to get a 3 in there. So we're going to have something factorial coming out. And in this case, 1 times 2, that is 2 factorial. 1 is a 1 factorial, so it is an n minus 1 factorial. So now we have those two pieces that we need. So we can write our sum. It's going to be the sum from n equals 0 to infinity of our nth derivative at 0. Now, this pattern is true for n greater than 0. When n is equal to 0, it's just equal to 0. So we are going to be breaking this up a little bit. So we are going to say that this is going to be f of 0 over 0 factorial times x minus 0 to the 0 plus the sum from n equals 1 to infinity of nth derivative at 0 divided by n factorial x minus 0 to the n. So this is going to be 0 plus the sum from n equals 1 to infinity. Our nth derivative is this. So we have a negative 1, 3 to the n, n minus 1 factorial divided by n factorial x to the n. So this is going to be equal to, let's pull that negative 1 out, negative 1 times the sum from n equals 1 to infinity of 3 to the n minus 1 factorial cancels with most of the n factorial, and we're left with just an n on the bottom. And this is our power series representation for the natural log of 1 minus 3n. That is going to be what that one would be. Let's see, let's find another one that we could do. Let's try and figure out which sequences will diverge. So our sequences are going to be a sub n equals 5n cubed plus 2 over n cubed minus n. We have a sub n is 4 to the n over 1 plus 7 to the n. We have a sub n equals cosine of n pi divided by n plus 3. We have a sub n equals the natural log of n over the natural log of 2n. We have a sub n equals 2n squared minus n over the square root of n cubed plus 3n squared. So which of these are going to diverge? Well, this first one that we have, well, this is going to be equal to 5 plus 2 over n cubed over 1 minus n over n cubed, which as n goes to infinity, this is going to go to 5. So that one converges. This next one is going to do a similar thing. This is going to go to 4/7. So this is behaving like 4/7 to the n, which is going to go to 0, so that one will converge. N pi over n plus 3, that is converging to pi, which means that this whole thing is going to converge to cosine of pi, and cosine of pi is going to -1, so this one will converge. This one is equal to the natural log of n over natural log of 2 plus the natural log of n, which is going to converge to 1. And then this last one, we are going to have to do a little bit of manipulation. So these values are always going to be positive for n greater than 0. So for n greater than or equal to 1, a sub n is strictly positive. So what this means is we can say that this is strictly bigger than, if we decrease the numerator, so 2n squared over the square root of n cubed plus 3n squared. Let's see, so we increase the numerator, whoops, I got this backwards. So that is less than that, which is not something that's going to be helpful for us. So instead of doing that, we are going to multiply the top and bottom by the largest denominator. So this is going to be multiplied by n to the, so 1 over n to the 3 halves, all over 1 over n to the 3 halves. So this is going to be equal to 2 times the square root of n minus 1 over the square root of n, all over the square root of n cubed plus 3n squared times 1 over n cubed. So this is going to be 2 square root of n minus 1 over the square root of n, all over the square root of 1 plus 3 over n. So as n goes to infinity, this is going to go to positive infinity, because we will get infinity minus 0 all over 1. So this one diverges. Let's see. Let's write down all of the different tests just so that you have them. I'm not in the mood to go through them all because they do take time, and since no one showed up, I will just go over them briefly and then talk about the things that I like more. So the different tests that we have. So we have the ratio test. We have the root test. Let's go over both of those real quick. So for the ratio test, we will let the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, we are going to let that equal to L. Whereas for the root test, we're going to let the limit as n goes to infinity of the nth root of absolute value of a sub n, we are going to let that be equal to L. So the ratio test says that if L is less than 1, then the sum of a sub n is absolutely convergent. Actually, this is the case for both of them, so I'm just going to put both of them in the same category. So if L is less than 1, the sum from n equals 1 to infinity of a sub n is absolutely convergent. If L is greater than 1, then the sum from n equals 1 to infinity of a sub n diverges. And the last case is if L equals 1, we got none. So if either of those limits are equal to 1, then the test told you nothing. You did the limit for no reason except for eliminating that as a test that would give us something. So if that's what you got nothing. So that's going to be how you can figure out those. Let's see, other tests that we got. We got the p-test. So the p-test has two different cases. So we have case 1. Well, actually, so the p-test has a couple different situations, and the p-test has is a name for 3 different tests for 3 slightly different things. So case 1, case 2, and case 3. Case 1 is for when we are looking at the sum from n equals 1 to infinity of, let's see, it is 1 over n to the p. That's what it is. 1 over n to the p. So here we are dealt with the situation if p is greater than 1, it'll converge. If p is less than or equal to 1, it diverges. So that's the p-test for series. The other two parts to the p-test, both of these are for integrals. But specifically, case 2 is for the integral from some constant to infinity, where this constant is bigger than 0, of 1 over x to the p dx. And case 3 is the integral from 0 to some constant, which is not infinity, of 1 over x to the p dx. In the first one, if p is bigger than 0, then this is going to converge. But if p is less than or equal to 0, it diverges. Notice the similarities in these two situations, because we are adding up a whole bunch of 1 over x to the p's, and both of these are starting at some finite value and then ending at infinity. So those two are tied together because of the relationship between series and integrals. Now this one is going to be different because this time we are starting at 0 and then going to infinity. So these are going to be sort of the opposite. If p is greater than or equal, not p bigger than 0 here. Those should be 1s. So here, for this last case, going from 0 to some finite value, if p is bigger than 1, it diverges. Actually, if p is greater than or equal to 1, it diverges. If p is less than 1, it'll converge. And if you're struggling to see the connection here, you could rewrite this in terms of like 1 over x's 2 powers, and then it would turn into case 2 again. But these are the 3 cases for the p-test. Let's see, we got the comparison test. So the comparison test has 2 situations again. So if 0 is less than or equal to a sub n is less than or equal to b sub n for all n, we now have 2 different things. We have if the sum of b sub n converges, then the sum of a sub n converges. Oops, we need a bit more space there. And then the other one, so 1 and 2, if the sum of a sub n diverges, then the sum of b sub n diverges. Notice those are the only 2 implications we have. We cannot go in this direction, and we cannot go in this direction. Those 2 directions are false. Those are not guaranteed to give us anything. Let's see, in addition to the comparison test, we also have what's called the limit comparison test. So the limit comparison test says that if we have the sum of a sub n and the sum of b sub n, and if the limit as n goes to infinity of a sub n over b sub n is equal to some constant and is less than infinity, and c is not equal to 0, then this says both the sum of a sub n and the sum of b sub n behave similarly. So this tells us that if the sum of a sub n diverges, then the sum of b sub n will also diverge. Or if the sum of b sub n converges, the sum of a sub n will converge. It just tells us that both of them do the same thing. So if you know one series and the limit comparison set test says that that series behaves the same as a series you're trying to tell something about, then both of them will behave exactly the same. So here, let me zoom out so you can see all of these at once, because these are the main tests that we have when we are dealing with these, and they are pretty useful to be able to do stuff with. Let's see, other things that we can talk about. Let's talk about Simpsons Rule for estimating something. So Simpsons Rule, this is somewhat useful if a bit confusing. Simpsons Rule. So this is if you were trying to approximate some curve like this. We're trying to approximate the area under that curve. We are going to break this up into n intervals. So we have n intervals, and then Simpsons Rule says that these, so like A to B, Simpsons Rule says that the area from A to B of our function f of x dx can be approximated by s sub n, where n is the number of intervals and we have the condition n is even. So s sub n, according to Simpsons Rule, is going to be delta x over 3, and remember delta x is equal to b minus a over n. So basically just what is the length of each of these intervals. So this length, that is going to be delta x. So delta x over 3 times this pretty weird looking thing, but I'll explain what it is in a bit. So it's going to be 1 of f of x naught plus 4 f of x1 plus 2 f of x2 plus 4 of f of x3 plus 2 of f of x4 plus ... until we get to a plus 4 f of x sub n minus 1 plus 1 f of x sub n. Now, this seems like it's coming out of left field. Like, where is this coming from? The idea of this is if we were to, instead of breaking, so let's draw a little picture so we can see it. So we have our function here, where it's doing something like this. We have broken this up into n pieces. If we, instead of breaking it into n pieces, we were to say, let's break this into n minus, or n over 2 pieces. So this is n minus 2 pieces. What Simpsons Rule says is if we were to weight each of these separately, so here are the different points we're looking at. If we were to take 1 of this one, 4 times this one, and 1 of this one. So we have, here's f of x0. Whoops, those aren't where f of x0 is. So down here we have x0, x1, x2. Up here this is going to be f of x0, f of x1, f of x2. Each of these pieces, if we were to look at so delta x, meaning this base, that is delta x. So if we have delta x over 3 times f of x naught plus 4 of x1 plus 1 of f of x2. What this gives us the approximation for is this gives us the area under the parabola that passes through those three pieces and then is under that curve. So this is approximating it not using rectangles, but by using areas under a parabola. And so what we do is if we add up all of these parabolas, which might not be super accurate, but we're getting decent parabolas. So if we were to get all of these different parabolas, that is what Simpsons Rule is approximating. And so if we were to add up all of these parabolas, notice that each of these points that are part of two different parabolas, so this one, this one, this one, we get one from this side and one from this side, so together they're going to get 2. So that's why the pattern goes 1, 4, 2, 4, 2, 4, 2, 4, 1. It's 1 on both ends because those are only part of one of the parabola approximations, and then all of these 2's are because they are part of two different parabolas. So that's what Simpsons Rule is coming from and why it's going to be kind of useful. It gets pretty accurate because of these parabolas, and so that's why it's going to be, on general, more accurate than the trapezoid or midpoint rules. Let's talk about some like surface areas and arc lengths, because those are fun as well. So let's start with arc length. So the arc length formula, the length of a curve, so there's f of x from f of a to f of b, our two endpoints. Arc length is going to be the integral from a to b of the square root of 1 plus f prime of x squared dx. So let's say, for example, that we were given an arc length problem. Let me find one that is fairly nice to do. Okay. Let's say that we are trying to find where f of x is equal to f of x is equal to x squared over 4 minus 1/2 the natural log of x. And we're trying to find from x equals 1 to x equals 2. So the length is going to be the integral from 1 to 2 of the square root of 1 plus the derivative of f, so that's going to be a 2x over 4 minus 1/2 times 1 over x squared dx. So this is the integral from 1 to 2 of the square root of 1 plus 0 squared. Because 2x over 4 is 1/2 x. 1/2 times 1 over x, also a 1/2. Oh, that's 1 over 2x. My mistake. So this is going to be 1/2 x minus 1 over 2x squared. And now we can go through and calculate this integral. So this is equal to the integral from 1 to 2 of the square root of 1 plus, this gives us a 1/4 x squared minus 1/4 plus 1 over 4x squared dx. So this is the integral. Let's pull out a 1/4 from everything. So that becomes integral from 1 to 2. The square root of a 4th is 1/2. Integral of 4 plus x squared minus 1 plus 1 over x squared. This is equal to integral from 1 to 2, the square root of, we got x squared plus 3 plus 1 over x squared dx. And then we would have to go through and figure out a way to integrate that, but that integral is going to give us the arc length of that curve. Surface area is pretty similar, especially if we are doing a surface area So surface area of an object of rotation. So we have, like, here is our x-axis, we have some function f that's doing this, and then we get that rotated about the x-axis. So we got this sort of shape here. The surface area is going to be related to, there we go, undo. So the surface area is related to arc length. So the surface area is related to arc length in that surface area is the integral from a to b of 2 pi times f of x times what was inside the arc length piece, 1 plus f prime of x squared dx. So if we were to break this up into the different pieces, we have the 2 pi radius times the length. So we're basically taking, if we are looking at a very thin slice, we have 2 pi r. This is like part of our circumference. So that gives us the circumference of these slices that we're looking at. And then we need to also have our height, which is this piece. It is the length of this segment here. So this is like our height. And so surface area is just circumference times height. It's adding up the lengths of a cylinder. So we're just adding up a whole bunch of cylinders that just happen to not be perfectly vertical, and that's where these height things are coming from. And so that's why the surface area of that is going to be what it is. The last thing I think I'm going to go over are centroids. So centroids. So we have some object, I don't know what it is, but we have some sort of shape here. The centroid is like the center of mass of all of it. So this would probably be about the center of mass if this was uniform. So the way to find those different pieces, so this is the point x bar, y bar, where we can say that the centroid is going to be where f of x is like measuring the density, equals f of x is equal to, so this is centroid of constant density. So f of x is measuring the height. So it's the height of the object. So the centroids, x bar, that is going to be the integral from a to b of x times f of x dx divided by the area. And then y bar, that's going to be the integral from a to b of 1/2 f of x squared dx all over the area. So those are how you would calculate the centroids of an object. I hope you enjoyed this video and that it was helpful for you. Please check out some of my other videos, and please like and subscribe if you have not already so I can continue to make these sorts of videos. Have a great day and good luck with the rest of your math.